we know that the thermodynamics or spontaneity of a reaction is directly related to the Gibbs free energy. So it's going to be really important that we understand how to break down the Gibbs free energy equation and know how to use it. All right? So in this video, what I'm going to do is I'm basically just going to describe every term and help you guys see how it relates to reactions. Okay? So the first thing, just going all the way back, Gibbs free energy, or delta G, is going to predict the favorability of the reaction. Okay? Remember that another word for favorability is spontaneity. All right? And it's comprised of three terms. It's comprised of the delta H, the delta S, and the T. So what I want to go through is just each one at a time and talk about what they mean. All right? So the delta H is the enthalpy. Okay? Enthalpy can get confusing because delta H and delta G, a lot of times they happen to be the same. A lot of times if you have a negative enthalpy, you'll also have a negative spontaneity. And a lot of students get confused thinking that they're actually the same thing. They're not. Okay? The delta H is just one component of the spontaneity, but we also have to take into account the temperature and the delta S, or the T and the delta S. So let me just start right there. Okay? What is the enthalpy? It's simply the sum of the bond dissociation energies for the reaction. So what that means is I'm going to be making bonds, I'm going to be breaking bonds. All of those actions require that I'm putting in energy or I'm receiving some energy. All right? When I add all those together, whatever my end number is, that's my enthalpy. All right? That's it. That's all it has to do with. All right? So, and later on, we're going to learn how to actually add and subtract that stuff. But for right now, I'm just trying to tell you guys the big picture. Okay? So, if something has a negative enthalpy, a negative delta H, that's what happens when you make bonds. Okay? When you make bonds, you are getting some energy back. Why? Because I already taught you guys. Remember that I showed you guys in the free energy diagram how you could gain energy by putting two atoms together. Okay? That's what we call exothermic. Okay? Exothermic doesn't always mean that the reaction is favored. Remember, favorability has to do with exergonic or endergonic. But it is one component of it. Okay? Well, what if your enthalpy is positive? If it's positive, that means I'm breaking bonds, because it requires energy to break bonds. Okay? Once you break bonds, that's going to be endothermic because of the fact that it requires that I'm putting energy into the system to make those atoms separate. Okay? That's all that enthalpy is. It's just the sum of these, the endothermic parts and the exothermic parts together. And then at the end, you see if the overall number is negative or positive. And that determines your delta H. So now let's talk about one that's actually a little bit more difficult to understand, is the entropy, the delta S. The entropy is a measure of disorder in the system. All right? And this can seem very confusing because it's like, how does the system know how disordered it is? I'm going to explain this in more depth later when I actually talk about entropy all on its own. But for right now, I just want you guys to know what the signs mean. And if it's negative entropy, that means that I'm going to a more ordered state. Okay, that means that I'm basically, entropy means how disordered something is, so it's the opposite of disordered, that's ordered. If it's positive, that means it's more disordered, okay? A state always wants to be in its most disordered arrangement possible, so that's going to be a good thing, okay? So when delta S is positive, that means my reaction is going to be a little bit more favored, all right? So hopefully you guys understand that negative means ordered, positive means disordered. Positive is the one that is actually favored, okay? Then finally, we have our last variable, which is temperature. And notice where temperature is in the equation. Temperature is going to be a coefficient of delta S. And what that means is that as temperature goes up, it's going to amplify the effect of entropy on my overall favorability. What that means is that as I jack up the temperature of my reaction, the entropy of the reaction is going to matter a whole lot more in determining the overall fate of my reaction, whether it's going to be favored or not. Okay? On the other hand, as I reduce my temperature down to 0 Kelvin or absolute zero, it's going to mean that my entropy becomes less and less important. Okay? Eventually, as you approach absolute zero, entropy doesn't matter at all anymore because there's actually no more movement, and all that matters is the heats of dissociation. Okay? That's kind of theoretical, but I hope that makes sense to you guys. We're going to be learning and talking about that more later when we discuss entropy all on its own.